Hello everyone and welcome into yet another live stream. And has it really been a while since last time we streamed on this channel. Let me first play some music in the background, by which I mean it's there we go. That's awfully loud. There we go. Hi there everyone. Hi, welcome to live streams, and hi Benzo. Hi, how you all doing? Welcome. Welcome to the hopefully last quantum mechanics live stream. I say hopefully because I'm really hoping that today we could finish up with just the Schrodinger's and uncertainty principle, and that's it. Just the only two things. Once we're done with those, we're done. That's it. I also haven't slept in how many hours now? 25, I think. So this is gonna be fun. Always up for quantum mechanics. Alex. Hi. This is great because we are just Schrodinger's and uncertainty principle, and uncertainty principle is pretty simple. It's the Schrodinger's that I'm mostly worried about. I will go with you on the last quantum mechanics stream as well. I think it was decent, wasn't it? I mean, so far every single live stream has been a success. Mommy's again speaking in camera. What do you mean speaking in camera? Hold on, let me just open everything up. Make sure we're all... What was the book we're using? The textbook? We're just... Was it Fitzpatrick or was it Fowler? I think it was Fitzpatrick. I know you can't see anything, give me a second, I'm opening stuff up. I'm not a professional. What is Hilbert space? Oh, yeah, we'll have to get into the mess today. Damn it. Yeah, now obviously, because it's quantum mechanics, we can't just drop into Schrodinger's equation and see what's up, because there's always so much more. Now, surprisingly, Schrodinger's equation is 12, and I'm pretty certain last time we finished on 2.8. I remember, I don't remember what they tell about particles. The third space of all possible states of a quantum mechanics system. As well as Hilbert spaces? Wait, what? Vector space of all possible states of a quantum mechanics system. Oh, them using vectors like mathematicians, not like physicists. Classical particles. I feel like we've been here before. Hold on, we have been here before. Yeah. This is basics. This is just a review of what we've done. Oh no, wait, because there is a V of P. Plane wave propagates so-called phase velocity. Okay, it's just phase velocity. Okay, we've been here before. Why am I getting a headache after seeing this? You're not alone, trust me. Oh, you're not alone. Wave packets. We've also been through wave packets, but I don't remember. I absolutely do not remember what they were all about. I'm pretty certain we'll finish around here, I think. So, cool. This is the final battle. Make it with 25 hours of sleep deprivation versus Schrodinger's equation. Let's go for it. Let's go, folks. In the first corner, someone who isn't a quantum physicist but plays one on TV. And the other corner, it's this mess. I mean, look at this. Look at this. Okay. Oh, fantastic. Oh, this is next. Wait. Oh, it's the exponential function. Wait, no, it's not. It's the x. Is it? All I remember about this function is that it's unbelievably complex and annoying. That's a massive red flag. If someone is using multiple letters in their function, that's a huge red flag. Okay, the previous discussion suggests that the wave function of a massive particle of momentum p energy E moving in the positive x direction can be written as this. No idea why can't any particle be written with this. Hi the PJR. I don't know why any particle can't be written down with this. I don't get why only massive particles could be written down, because it really seems to me like this is just the complex amplitude, and this then would be just a wave function. I don't know. I know. I'm not gonna question. Where k is equal to p divided by h bar, which means k is the wave number, is equal to momentum divided by h bar, which is a constant, is greater than 0. Okay. Can you talk about complex functions? There is not much to say about complex functions. They are just boring. They are just straight up boring. They return a complex number and that is it. It's convoluted, it's complicated, but there is no actual meaning behind it. Something you make it. How did you learn mathematics? Do you have any tips? Going deep. That's it. Just start with quantum mechanics and usually it works. So why does it exist? Because mathematicians like it for some reason. Okay, complex numbers are more convenient to describe waves, and that's the only reason. Yeah. So it really is because mathematicians like it. When should we expect the new video? Anywhere from 3 to 5 days from now. It could be in 2 days. It could be tomorrow. Well, it won't be tomorrow, but it could be. I have no idea. All I know is that I'm making progress and I'm working on a lot of videos. So there are a lot of videos coming. It's just I am also working on a charity, and in 2 days you also see a new format of live streams. And trust me, I'm working, alright? I'm busy. I'm trying my best. Okay, here omega and k are linked via dispersion relation. What now? Oh, it's a wave bucket thing. 238. Oh, this links to itself. This? I don't... Hello, thanks for putting into your work. Cheers from India. I really appreciate like you'll appreciate it. I guess, yeah, it's, I mean, it is. But that's why I want to actually take some additional time for this new video. I want it to be right and great and correct and solid. Rock solid. Okay, expression represents a plane wave whose maxima and minima propagate in the positive x direction with a phase velocity equal to omega divided by k, which we've seen one chapter ago. As we've seen, this phase velocity is only half of the classical velocity of a massive particle. Well, I missed that part. Whoops. That's the key, I suppose. Previous dispersion relation, a particle plane wave propagates up. So particle plane waves are different. Okay, got our yeah. How do you stay motivated to learn physics? Caffeine, coffee, caffeine pills. Will there be more lives today? I know I have to take. Listen, I'm really tired. I'm really tired. But there will be new one tomorrow, and tomorrow I'm actually gonna start earlier on, and I'll do a walk live stream. Walk live streams are never truly walk live streams. They're just math live streams masquerading as Blender animations. So, but if I finish this, that means I can finish this full script for the quantum mechanics video today. Okay, so if I research this, then after the live stream I can finish the script, and then tomorrow I can make an animation live stream where I'll just animate everything I need. And once all the animations are said and done, the video, yeah, I can just make a video in 2 hours. I really love the addition to quantum mechanics vid. Gotta say, you're the first YouTuber I instantly subscribe. I should learn English, but this is way more interesting. First of all, I don't know what you're talking about. Your English seems really fine. Really love your audition. You gotta say, you're the first. You used the "your" correctly, which, well, most English speakers can't do that. This is way more interesting. Well, I'm also right now working on another quantum mechanics video. This one focused more on the actual quantum mechanics, because I can't stress enough just how basic the addition to quantum mechanics really was. That's mostly because I went over, well, everything from addition to quantum mechanics, so yeah, it had to be basic. Me who can barely handle simple harmonic motion. But isn't like harmonic motion more difficult than this? Harmonic motion. Hold on now. Harmonic motion, this periodic motion, object resonant force. I mean, this isn't much more complex than. It's actually much easier than this, and isn't much more complex than this. Why am I saying Indian? There are actually plenty of Indian people watching my videos. I think it's the third highest audience by country, I'm pretty certain. I'm pretty certain that harmonic motion is just a similar level of complexity, actually. I mean, here you have f is equal to derivative of mv. Here you have integral, which is derivative the other way. So like... Hi, debris, by the way. Alright, so expression, as we've seen, place velocity is only half the essential of classical velocity mod. Okay, so this is only half the velocity. So we have phase velocity. Plane wave propagates at so-called phase velocity. However, according to the previous dispersion relation, by the way, great name, I've got to say, dispersion relation, particle plane wave propagates at this. So, distinction between a plane wave and a particle plane wave. Particle movements in 3 dimension, we have the relation. Okay, so momentum of a quantum particle and hence velocity is always parallel to its wave vector. Yeah. Momentum wave number applies to both photons and mass particles. It seems plausible that the closely related relation 261 was it? Okay. This energy is equal to h bar omega, which basically states that energy is based on the frequency. Oh, we just copied it right here. Okay. Between energy and wave angular frequency should also apply to both photons and particles. In this case, we can write this for particle waves. The equations 292 and 296. So this one. The following dispersion relations for such waves. Okay, so let's see it in action, right? Because numbers are far and all when they are confusing, but let's tame them a bit. Let's actually walk through this and see what they're actually telling us, okay? So first of all, y'all might remember that we have E is equal to h bar omega. And yes, that is, you are right, that is absolutely tiny text. Let's just... Ali! Oh, hi there, Ali. How you doing? How's your day going? Alright, so energy is equal to h bar omega, which basically tells us that energy is related to the frequency, right? This is for massless. This is the equation for massless particles because, as you may see, it very conveniently leaves out mass. There is no mass, right? This is frequency, this is a constant, this is energy, there is no m. Now we don't have to go walk around this with massful, I suppose, particles, I don't know what to call them. Because with massful particles, we can just plug in mass. So, p squared and then 2m. I'm on a break, I've been super productive with my classes at work. That's great to hear. I'm very glad to hear that. What's the goal of the stream? To understand the Schrodinger's equation. The uncertainty principle I already kind of get. Thanks to the help of the wonderful Alex, I actually was able to fact check my crazy theories and realize that like 1 or 2 of them actually were how things actually worked. So so yeah, thanks to Alex, I understand uncertainty principle enough to actually script it. That's not an issue, but I don't understand the Schrodinger's equation enough. I know it's about the curvature in relation to energy, the kinetic and potential. I do and have a good stream. Oh, are you French speaker? Not in French. How do you manage the consistency in making videos? Lack of a social life helps. Let me show you something. Let me show you just how mentally stable I am. Let me show you my spreadsheets. So we have two important spreadsheets here. What is the Schrodinger's equation? We'll get to that soon. This is actually... Okay, when it comes to Schrodinger's equation, we have to get into it in order to actually explore what it says. First of all, this. So if you want to see just how productive I've been today, I haven't been all that productive. If we scroll back, let me scroll down a bit. As you can see, I spent like 2 hours today just resting because I had a tiny little bit of a mental breakdown. On the beginning, I also spent a bit of resting and I actually woke up yesterday at 8 PM. It is currently 9. Yeah, so I've been awake for 25 hours. Well, I only know about the Schrodinger's cat. Schrodinger's cat comes from the uncertainty principle, not the Schrodinger's equation. Confusing stuff. I could also explain the uncertainty principle, I suppose. It wouldn't be that difficult. So this is the first thing, my progress tracker. And second one is this. This one tells me what the percentage of videos I need done. This one tells me the percentage of the videos already done. So far I finished 3% of the videos. Hooray, I suppose, right? Well, 3% of the work required to make all of the videos. I plan on making 17 videos in the next 100 days. That's why I have to get back to work. Alright, my point is, here's the thing. When we have a massless particle, we can use this equation to describe its energy in relation to the frequency. The reason why we don't use this equation is very simple. Because for a massless particle, right, this equation would basically look like this. And for all of you who skipped math classes, I should mention that dividing a number by a multiplier of 0 is not a good idea. It's actually pretty bad. It's not that great. That's why we use this equation instead for massless particles. Makes sense. This we can use for massful particles. Alright. Next video, Schrodinger's equation, quantum mechanics. It will conclude with a Schrodinger's equation. This man is living my dream productive life. Everything at a cost. Ayash, trust me, it's not fun. How does a particle have zero mass? That's a wonderful question. Actually, the answer is simple. Well, I could give you just an example of a photon, I suppose. How can a particle have zero mass is... Well, the thing is, mass is not the requirement for a particle. Energy is the requirement for a particle. Right? That's what you need. You need energy in order to... I love the... Okay, there's one thing which I love, which is E equals mc squared. I absolutely love this equation. Not because of the energy to mass conversion, no. The reason why I love it is that it showcases just how C is basically the infinity of the universe. Because for photons, for example, this would be 0 times C squared. I just really like that bit. And like massless things kind of break in theory, but in practice they don't. But isn't energy also mass? Yeah, it is, as I mentioned, right? E equals mc squared. Yes, conversion of mass to energy, that is true. But that's why, like, the requirement of a particle is energy, not... Okay, the requirement of a particle, my point is energy, not mass. So when you have a particle which has mass, then you can use this equation to conclude that it also will have energy. If a particle does not have mass, you can use this equation to determine that based on its frequency, it also will have energy. So we have equations for a mass, well, mass I suppose, massless particle, alright. Massless and massful. And then just massive. Any questions? This should explain it pretty well. Now, let's go on. So, light particle properties. It turns out that massive particles sometimes exhibit wave-like properties. It's possible to obtain a double-slit fringe pattern from a stream of mono-energetic electrons passing through two closely spaced narrow slits. Effective wavelength of electrons can determine measuring the width of light. Yeah, okay, so that's great, which means that particles with mass also walk like waves. W conclusion. Thank you, sandwich. Yo, I should stick to normal addition. Frequency times Planck's constant is equal to, for example, a photon's energy. With this equation, it doesn't need mass. Yeah, I mean, if you think about it, it makes sense. I'm coming here for homework help, not gonna lie. I don't know if I'm gonna be much of a help. Let me explain why it makes sense, okay? Let me show you why it makes sense. So, basically, we have two rules, alright? Two of them. That's all we need, two rules. Or maybe even one rule. Let's just add one, we'll see where it goes. If, in order for something to have a velocity of c, right? So, if velocity of an object is equal to the speed of light, then its mass has to be equal to 0, alright? So mass has to be equal to 0 if velocity is equal to the speed of light. Also, Tegate, you can just go to the Discord server. We have a whole forum dedicated to just helping. Hi, Denana, by the way. Yeah, okay, so do we all? But why though? Well, the reason is I'm pretty certain, not 100% certain, but if I remember correctly, relativistic time dilation. Could this be the reason? I think so. If you have this, no, it wouldn't be time dilation. Would be wait, hold on. Basically, when it comes to relativistic physics, as it turns out, the higher the velocity, the more confusing the math gets. So, like, if you have this, then, for example, at the speed of light, the time is equal to, get this, 1 minus speed of light squared divided by speed of light squared, which equals 1 minus 1, which equals square root of 0. Which means that at the speed of light, time is like 0. Okay? Hi there, Hans. Oh yeah, you haven't been here a while, I suppose. That's the viewership for these new live streams now. Science live streams are great. I love science live streams. This is just something that we kind of have to accept, because if you're looking for explanation for why this happens, right? Why is the speed of light the maximum? The answer is, it just is, alright? That's just the way universe works. It's kind of like asking, why is matter a thing? Well, matter is a thing because it's a thing. Okay? It's like the underlying rule of the universe. Why is speed of light the maximum? Well, because it is. I mean, you just can't go past it. Okay? So, this is our first thing which we have to accept. If velocity of particles is equal to c, then their mass has to be equal to 0. Okay? Don't Maxwell equations prove that the speed of light is unchangeable? I'd love to see a video about that. Actually, the relativistic... if I were to make a video about relativity, I could just animate the crap out of speed of light. It would be lovely. Conclusion of the stream, it is what it is. Yeah, it is what it is. We just have to accept this, right? I would love to make a relativity video, it's just I have a lot of things on my plate. But I will, couple of months. or maybe weeks if I'm, I don't know, lucky or something. And also prove that if you have non-zero mass, it would take infinite energy to get the speed of light. Yes, and that's kind of the, well, that's the momentum bit, which is this one. So momentum. Okay, so here's the $1,000,000 equation. E is equal to p squared divided by 2 mass, alright? E is equal to p squared divided by 2 mass. If we have our photon zooming through space, okay, at the speed of light equal to c, with its mass equal to 0, then if we plug this into the equation, we get a bit of a problem, like a little bit of a problem. Momentum equation. Let me show you the momentum equation real quick. Alright, so momentum is equal to mass times velocity, which means right here we get mass times velocity squared divided by 2 mass. Now this is really convenient because we have mass squared times velocity squared divided by 2 mass, which is great because these two cancel each other out and we end up with mass velocity squared 2, which I'm pretty certain is the equation for kinetic energy. Do you do YouTube as a full-time job or are you doing something else? Yeah, I do freelance CGI art stuff and I hate it, it's awful. Mass was the best descriptor I've ever seen. YouTube earns him like no money. No, it's not no money, it's $2 a day. It's like what, one... Well, in California it would be... wait, this times... So 30 times 4... In California it would be 1/60th of a minimum wage, if I'm not mistaken. It's not no money, it's just not a lot. Okay, this, right? Now why is this an issue? This is an issue because the speed of our particle is equal to c squared. And the mass of our particle is equal to 0 because the photon has no mass. Which is a problem because, as I mentioned, speed of light is kind of, alright, the infinity of our universe. In most ways, it's basically the speed limit. It's just the infinity, okay? Which means that what we kind of get from this equation, this is obviously not a mathematical thing, it's just like, as from the perspective of the universe, what we get is 0 multiplied by infinity squared. Which don't make much sense now, does it? Do it be making sense? The answer, no, it do not be making sense. How can you have a 0? How can you multiply it by infinity squared? What are you supposed to get? Why are we even dividing by 2? Are we even bothering? It's 0 by infinity. There, it's over. Which means that we can't apply this equation to photons because it's gonna screw everything up. So instead, because of some boring math for nerds, which we went over in the previous couple of live streams, we can also end up with this equation. E is equal to h bar omega. And oh boy, isn't this an amazing equation. Why? What is omega? Well, I'm so glad no one asked. Omega is the frequency. Well, something related to frequency. It's angular frequency, whatever. It's some BS. The point is, right now, we can tell that our wave particle, right? Wave particle, okay? Its frequency, so sort of wavelength in time, okay, is related to energy. It's actually proportional to energy. Now normally would be a problem because we're dealing with particles, but right here you might notice like a sneaky little thing, like a sneaky little back door, you know, like a way for us to cheat the system a bit, like a very sneaky plan to actually go behind and fix the issue. I wanna lie, but sounding really silly right now. It's only. But you're sounding really silly right now. It's only. No, but I'm not, because if you actually take a look at all the equations, they all treat it as infinity. Like, for example, this one. Or, for example, well, practically every single equation from the relativity, actually. They all treat it as the maximum. You can't go past it. Okay, so it's like an infinity of the universe. And for example, no, mass is not massing. I'm thinking of shifting to oh, I would love to live in the Netherlands. Netherlands, amazing. Infinity of the universe, he's using that term because it's a speed that is not possible to reach. Just like no matter how high you can't reach infinity. Precisely. Watch Nana, you get me. Yeah, it's nice to have a real one in the chat. Why is omega both angular frequency and angular velocity? It is because angles. Scientists run out of letters, honestly. Greek alphabet doesn't have enough, so reduce, reuse, recycle letters. What do you like about Netherlands? Oh, I'm guessing you. Okay, well, wave, trance music, everything. Yeah, it's made by Soda KC Music on YouTube. Would recommend, link in the description. Everything but real knowledge. Yeah, the omega thing confused me as well. Our professor used two different ways to write omega to make it more sense. First of all, make it hilarious, because that's what I'm called. But at the same time, yeah, the scientists just are awful with notation. Like, they use this to represent a function most of the time. And they completely fudging forget that there are, like, inputs that are supposed to go into the function. Who cares about those bits, right? It's a proper character, isn't it gonna confuse anyone? Angular frequency and angular velocity are also the same thing, yeah. I suppose that... Well, there we go. Listen to Alex. Alex actually knows what we're talking about, so yeah. There we go, that's the way they use omega for both. We have equations with 0 and nothing multiplied by infinity, kind of everything. Yeah, that's basically what we're doing here. That's basically the problem with this. Well, the main issue actually happens because the momentum is very much dependent on the mass. So in this case, you know, it's gonna screw us over a bit. But here's the basic idea. With this equation, we can calculate actually energy for massless particles. And what's really, really nice is that from this, we can actually get momentum. Now you might be obviously asking me, make it, but how could we possibly get momentum? This doesn't make any sense. I mean, momentum, alright, is very clearly just mass multiplied by velocity. But when the mass is equal to 0, then the momentum will always be equal to 0. So why would we ever get momentum? This doesn't make any sense, does it now? And that's it. And you know what I've got? I know I'd say, well, aren't you just a little clever? Aren't you just a little clever classical physicist? But we're not here to make reasonable classical mechanics. No. We're here to do mad and batshit crazy quantum mechanics. So instead of giving up and being like, oh well, I guess mass is equal to 0, there is no momentum, we say, well, since we can calculate energy, and main thing on momentum is kind of just, it's mostly just about kinetic energy, then there surely has to be a way to get momentum of a massless particle. And we won't believe it, but like, there absolutely is. If we scroll up a bit more, and then some more, we get this. Momentum is equal to energy divided by the speed of light. Can't wait to use an indefinite integral to calculate velocity. Hashtag quantum mechanics things. But to be fair, you would also do it in classical mechanics if you want to be exact. Like that, okay, that's just precise physics thing. Well, I'm learning that functions are written as f of x. They make it convert trident function without the... yeah, because but I'm complaining about the same thing. The main... Okay, the thing that pisses me off is not that they use psi. That's perfectly fine. It's standard notation at this point. You have capital psi with time, lowercase with no time. It's great. What pisses me off is that they don't use the brackets. And this confuses people, which is reasonable. We associate brackets with being functions. It's kind of like creating an operator. Okay, this might be something that only Alex would get because this is an actual mechanic thing. It's kind of like creating a make it operator and then only adding hat on top of it whenever I feel like it. So I just basically would input M. Oh, is this mass? No, it's an operator, but I just kind of forgot to put a hat. Deal with it. It's really annoying, the inconsistency. Deep breaths, man, deep breaths. Oh, don't even get me started on the different notations. Don't even get me started on the derivation by parts with the X and Y in the Greek alphabet. Now I need to know if Alex got that. Yeah, I also actually would need a fact check. Drink some water. I don't have any water. Water for suckers. I drink liquefied caffeine, concentrated, taken up. I want? Nope, it's just a scam made out by bedroom companies to sell more bedrooms. Non-stream. Non-stream sounds like a banger idea. Stream? No. You all do realize that in 2 days we'll be doing the 400 child checkup, by the way, right? 2 days. In 2 days, 400. I wasn't actually doing it, but I wasn't actually advertising it, though. But I guess I should. It's gonna be an awesome stream. Yeah, for real, on God, no cap. Alright? I'm excited. So am I! Karaoke stream for day 400. I have something really cool planned, which either is gonna be a massive failure or a massive success, no in between. So I guess we'll see. Alright, what was I thinking about? Oh yeah, right, so that's all the math we need to catch up, actually. Now we can get back to research. I wanna learn, keep going. You know what, happy, I agree. Let's keep going. So, yeah. What's next? How can we write the wave function of a particle that's localized in X? That is, a particle that is more likely to be found in some position on the X-axis than others. It turns out we can achieve this goal by forming a linear combination of plane waves of neighbor numbers. Wait, hold on, what now? More likely to be found at some positions on the X-axis than others. I mean, a particle's line? Oh, you have 500 tabs and applications open. Wait till you see my other screen. Hold on, let me see if I can... I have so many things open on the other screen. On the other desktop, I mean. I have technically 4 different screens open. How many monitors? Well, 2 monitors, but also 2 desktops environments. Desktop environments. Alright, so... How can you write the wave function of a particle that is localized in X? That is, the particle is more likely to be found at some position on the X-axis than others. It turns out that we can achieve this goal by forming a linear combination of plane waves of different wave numbers. In other words, I don't understand what this means. And this is a function all of a sudden! I feel like I am the only sane person in Crazyville. Like, I'm not insane, am I? This one doesn't have brackets. This one does. I was introduced to this as notation for a complex amplitude, which I had no idea I took input. Since when is that a thing? This man is looking. Yeah, I am. I very much am. Doesn't make any sense. And that's what pisses. Remember the thing I mentioned like a couple seconds ago about like how they use notation willy-nilly and they only input the brackets when they feel like it. You sum up different waves of unique frequencies, but for stuff that is not discrete, you didn't integrals of some. Okay, you sum up many different waves of unique frequencies, but for stuff that's not discrete, you do an integral instead of a sum. Okay, makes sense. So basically, oh, it's decay. First of all, didn't notice that. Very important, I suppose. We're integrating in relation to the wave number, not the position, which makes sense. We can form a linear combination of plane waves. So, just wait till we get the complicated part. Yeah, I know. How do you know stuff? Alex is a pro. Alex is a professional. Alright, so it turns out by forming a linear combination of plane waves of different wave numbers. So yeah, we have. Do you work for the government? Why is that your first question? Alex, are you a Fed? You know a bit. You seem to know a bit too much about quantum mechanics. Are you perchance a Fed? Anyway, so it turns out we can achieve this goal by forming a linear combination of plane waves of different wave numbers. So, okay, linear combination is a fancy word of an integral, I'm assuming. And plane waves of different wave numbers. So yeah, we basically integrate. I still have no idea what this is actually. I don't know what this is. It looks like an angular, like a complex amplitude, but apparently it's not. What the heck is sign for hat? This is not a hat, this is a bar. Difference is important. Hat is used for operators. Bar is used for whatever anyone feels like. I don't know what bar is used for. Alternate constants, I think? Classical invariance for electric, classical light waves. I think this one. It's like a weight factor for different frequencies / wave numbers. Weight factor for different frequencies / wave numbers. Wait, so is it the complex amplitude or not? Because here we have the complex amplitude with psi 0. Although, I'm pretty certain in the very next chapter, make some waves contribute more strongly than others, so it's both. Okay. We have this. And then we have this, kr omega t, kx omega t. Ooh. Is that the difference? Well, no, because right here, okay, kx omega t minus IE. Okay, so this, yeah, they just replaced 0 with a bar, because why not at this point? So it is the complex amplitude, which is used to factor for different frequencies / wave numbers. It's like a weight factor for different waves. So make some waves contribute more strongly than others. Okay, so this is complex amplitude, which is made to make some waves contribute more strongly than others. Alright, which means that we just input the wave number, and this makes waves of a certain wave number contribute more strongly than other waves of a different wave number. Oh, here represents complex amplitude of plane waves of wave number k in this combination. Okay, so this k is just a complex amplitude for each wave of a different wave number. That is always possible to add two valid wave solution to form a third wave solution. possible, yeah. The ultimate justification for this assumption is that particle waves satisfy a differential wave equation that is linear in psi. As we shall see, this is indeed the case. It is indeed a plane wave that varies as and has negative k but positive omega, propagates in the negative x direction, phase velocity of omega divided by k absolute. As this with position goes both forward. Okay, there's useful mathematical theorem known as Fourier transforms, which states that if this mess, then this mess. And right here we have a bar, right here we don't have a bar, and the negative also switches. I'm assuming it's because hence it's a Fourier transform of function f of x. Okay, so it's just a Fourier transform. Makes sense. Sick. Oh. I give you one suggestion. Just copy this formula and paste in text-based AI like ChatGPT and tell them to explain only terms of this formula. I guarantee you understand by reading terms. No, because this... Not in this case. Because I know what terms are. I know what these terms are. I really do. This is just... Okay. Complex amplitude, wave number, angular frequency, I think is what it's called. We have the wave function with the time and position. It's not that complex. It's just straight up hard. I suppose that at time 0 the wave function of a particle takes the form. Okay, so at initial time, how does it roll, by the way? Only be like 2 seconds, but I've only got the stream again. Cool. Okay, so we have psi at 0 time, so the initial time, right? It's proportional to this. In this case, I should read the explanation first before assuming. Why is E in there? Mate, that's your question? Wait, where you saying E? There's no E. Oh, you mean this one? Mate, you saw this. And your question is, why is E in there? Okay. K0, okay, right, this is called Gaussian distribution and is plotted in figure F4. It can be seen that the measurement of the particle's position is most likely to yield value x0 and very unlikely to yield a value which differs from x0 by more than 3 delta x. Thus, equation. This is the wave function of a particle that's initially localized around x is equal to x0 in some region whose width is of offset delta x. This is type of wave function is known as a wave packet. So we got to what wave packet is. That's great. So it's just the type of wave function. Wait, so wave packet would be just like the wave in which the probability of finding a particle would be mostly centered around a certain point. I guess, I think. Most likely to yield value x0 is very unlikely to yield value which differs from x0 by more than 3 delta x. So yeah, I think so, yep. Okay, sick. Alright, that's actually a very simple concept. Okay, cool. So wave packet is actually really simple. Just going back to our blender for a second. If we imagine, hold on, no, don't save. If we imagine, I don't know, plane, right? Scale it up a bit. Then give me my dearest cycles. Let's shade it up a bit. We'll be doing it in 2-dimensional. So we squish it down around a certain point. Okay, yes, so texture coordinate. This vector map, I suppose. Not divide, only distance. In 2 dimensions, oh damn it, math, divide, where's 0, 0? Wait, what? Hold on, I'm gonna figure this out, don't worry. Don't worry, I'm a smart boy. There. 2-dimensional wave packet, I suppose. Kind of. It's not really Gaussian. Good. Kind of. There. Sit. Yeah. I had always one question in my mind. Quantum particle behave like waves, but when you measure it, suddenly behaves like a normal particle. Why is that? Wave-particle duality. It's the law. Is actually I feel like it's that perfect response actually. So this is very annoying because this is not just theory that scientists made up for some reason. This is just how they found the universe to work. Okay? In math, everything has an explanation. We have a reason for everything because we are making the rules. In quantum mechanics, it's different. It's the universe making the rules and we have to follow them. That's why when it comes to quantum mechanics, we just have to accept the wave-particle duality. It may not make sense, but that's just the way particles behave. And that's kind of it. There's not a satisfying answer, but it's a true one. Okay, so according to this equation, some BS, hence we apply for the transform to invert this equation to give this. Is bar a Fourier wait, hold on, what? Wait, is psi bar of k a Fourier transform of the wave function? You have particles that exist and don't exist. I forgot the name. The superposition, you mean? What you looking for? Okay, so no. Particles that exist and don't exist. I don't know. Particles that exist and don't exist. Yeah, I know. And anyhow, here we have some more BS, but this one seems kind of cool because it looks like a bar actually means a Fourier transform, which would be kind of neat. Making use the equation, we obtained that the I think it's Fourier transform. Bar is Fourier. All right, cool. We're back into standards town. That's my strong suit. I'm good with these because they don't need that much thinking. You just know what things mean, which means that Fourier transform of the wave function is proportional to this mess, which I'm guessing is just the applied wave function. I mean the applied Fourier transform. Now making use of this equation. Which equation is that? E to 45. No idea. The stream. Watching this stream. What do you mean, Ash? What do you mean? What if light is a different dimension particle? It's a very specific kind of question. Because from a mathematical point of view, not much is really changing. I mean, you just add one more number. Yeah, it's a very odd kind of... Because from a mathematical point of view, we can just calculate it and... Yeah, you just add one more number. but you don't have to change the behavior of particles. It's just that in that case, light, all of the visible light for us would have velocity equal to 0 along the fourth dimension. Okay, changing variable integration to y is equal to, yeah, whatever. This is just math. This is just advanced math, which is kind of boring. If I was better at math, it maybe wouldn't be, but we would then spend 30 minutes just solving it. So, where beta is equal to this, equation can be rearranged to give this, where, yeah, integral now just reduces the number as we can see, make it a variable. Hence, we obtain cool meat. Hey Ash, are you drunk? Make it. Are you thinking of explaining how big plants? I can say starts. How big plants I can say starts a band light? Presume starts bent light? Explaining how big planets I can say stars bend light any day? I don't understand exactly. How big planets bend light? Planets, yeah, big planets bend light. Well, I mean, bending light, it's not... Is that interesting? This is gravity, isn't it? Could be a reason why it behaves like a wave when not observed, but it doesn't behave like a particle. We just don't know why. There's like magic, which is not... It's like magic, which is not real, I hope. You have to remember that, okay, it may seem like magic, but what is your reason against this sort of thing? You have to remember that if it's behaving this way, that means there either is an underlying thing causing it to behave this way, and then we would basically keep on going with further questions. What's causing the underlying thing to behave a certain way? The thing is, this is just like a fact. It's kind of like wondering. It's kind of like wondering why mass is massive. Wondering why photons behave like a wave and a particle is kind of like wondering why mass is massive. Which is... it's difficult for me to answer. A long discussion if you could argue the weirdness of quantum mechanics away by some analytical classical physics that end the so-called Bell inequality in the way. Yeah, it's just a mess. That's my comprehensive summary of the subject. Alright. Why is it changing when I click on it? Huh, fun. If the proportional to probability is proportional to the probability density of a measurement of a particle's position yielding the value x, then it stands to reason that the Fourier is proportional to the probability density of measurement of the particle's wave number yielding the value k. Okay. According to the equation, proportion, yeah, note that this probability distribution is in a Gaussian k space. Entity measurement k. This is uncertain. Are we laying groundwork for the uncertainty principle, or am I? It really seems like it with the Fourier transform. This seems to be unsatisfied. Now I know how my room feels. JK, I'll have one. I'm trying to understand quantum mechanics. Spoilers. Oh no, did I spoil it? Did I spoil the uncertainty principle? Oh no. You won't believe it, but it's about uncertainty. Not that probability distribution, okay, yeah, boring math nerd stuff. It's a measurement of k is more likely to yield value k0 and very unlikely to yield value which differs from k0 by more than 3 delta k. Incidentally, a Gaussian is only simple mathematical function in X space, has the same form as Fourier transform. Okay, I'm not going to include all of the math in the video. Okay, hold on, I was moving my microphone. I'm not going to include all of this math in the video because unless you really like math, this is just straight up boring. The thing, it's important, not denying that, it's important math, very important. And I will certainly link this as a major, okay, to say a major source is not say enough. I will certainly showcase a couple of things, but I won't really link up this math because unless you really like math, this will be so boring to you. And I already made an example for the uncertainty principle, and I'm really proud of it. Property wave packets, namely, if we wish to construct a packet that is very localized in X space, we'll need to combine plane waves of very wide range of different K values. Conversely, if we only combine plane waves with wave numbers differ by a small amount, the resulting wave packet will be extended in X space. What? You mean to tell me that you can't at the same time precisely measure the position and wave number of a particle? Alex, did you know about that? That there's like this weird thing where you can't really measure the position and wave number. It's like a, I don't know what to call it. It's like a lack of certainty. What that? I wonder if there's a word for it. Maybe. Can you believe it? Never heard of it. Yeah, me neither. Apparently it's a thing. Well, isn't that? I'm uncertain of what to call it. Yeah. I mean, it feels like a pretty important principle. Like a lack of certainty principle, I don't know, but I mean, I might be the first one to ever coin the name. It's crazy. That's crazy. What's really crazy, honestly. Obviously, this is a feeling. How can you explain? I will in a second. What's really crazy to me that this is let's call it the no-no theorem. That's a much better name. But what's really crazy to me is that they explained that Fitzpatrick just explained masterfully, from a heavy mathematics perspective, explained the uncertainty principle in a chapter that isn't even about the uncertainty principle, which is just incredible in my opinion. Basic idea. Is there such thing as a basic idea at this point? Well, children, well, it's time to learn a thing or two about our girlfriend, the Fourier transform. Yay! Fourier transform in Desmos. Graphically, actually, I've made a wonderful example of... maybe I shouldn't, yeah. Actually, I have an unbelievably cool example which I made and I'm so proud of it. It's my crown jewel of explanations because I made it a while back. I'm really happy with it. Yeah, I never actually got to share it that much, but I'm really happy. It's better first look at Fourier series and then go to the integral version. Maybe, but I'm actually trying to... Okay, I actually want to do it without explaining Fourier transform. That's how good I am, alright? That's how cool I can... Listen, I can explain the uncertainty principle without explaining the Fourier transform. Okay? It's definitely not because I'm actually running out of time. That's certainly not the reason. So here's the thing. Let's imagine a simple function which may look complex, but trust me on this, it is simple. For s squared t, oh yeah, I forgot s squared t, s pi and e to the power negative 1/2 x divided by s squared 10 cosine, wait, no, not the 10 I meant, 10 cosine x. Now, y'all may be asking, make it, what the heck are you talking about? How is this simple? It's like a mess, right? It's insane. And well, yeah, it certainly would if you're looking at this from this perspective. In reality, it's actually really simple if you divide it into two parts. So now we have the 10 cosine A function, right? 10 cosine, which is just going... It's a cosine function, multiplied by 10. It's trivially simple. And then we also have this monstrosity. Which is dependent on the s. If we move s from 0 to 100, then we can move s around and... Actually, you know what? I should probably input the 10 right here. This is much more important to scale. And there we go. That's what it does. It just... Like, you can all see the I mean, yeah, there's no point for me to explain it. Just look at it. That's what it does. It's... Any questions how this function works? I don't really think there's a solid way for me to explain how this works. I mean, just look how changing ds affects it. This shape of the function is what we care about, and yeah. Put a 3 into the cosine, I mean 3 cosine x? Wait, why? Why 3? I'm gonna shorten it a bit. This is an excuse to show us a funny graph. You better believe it's an excuse. This entire video is an excuse to show us a funny graph. Why make it? That's cool, but how do you make it look like that? How does it work? Well, I'm so glad you asked. The product of FND. Yeah, so here's the thing. This is our... I like to call it a factor and a wave. So here's how multiplying... So we have this function d, which basically tells us just how important a function is in a certain area. So right now we can see that the function is very important right here, but not that important on the edges. So if we have, for example, a function like x7, 7x, it's going really high up really quickly. But when we multiply it by the d of x, this is what we get. Why? Because if we align over the initial x function, 7x, we can see that it actually correlates strongly in this area where this function is actually pretty high. But right here is going back to 0 as this function is going back to 0. This is not making it any clearer, is it? Hold on, let me cook for a second. Let me think. Maybe I should just jump straight to cosine with this. So we have two functions, right? The purple one and the green one. Okay? Well, this seems complicated. I'm gonna waste my life on it. 3 in the cosine. Do we really need to put 3 in the cosine? I mean, this seems to work just fine. Fine, Alex. But only because I like you. There we go. Does this make more sense? No? Well, I get it. Wait, do you really? I'm impressed then. If you get how this works, I'm impressed. Mostly because I haven't actually explained anything, which means that just based on the graphic, you actually understand how this works. I mean, okay, the concept isn't that complex, right? We just have this function which scales the cosine. That's it. 3 always helps. You know what? I agree. It just scales the function a bit, right? Yeah, precisely. That's all it does. Yeah, that's the entire idea. But here's the thing. This is actually pretty great for showcasing how wave functions work. So let's say we have a wave function like this, right? Let me ask you a question. What is this wave function's wavelength? Alright? Now, you, the smart boy you are, what you can do is you can just screenshot the thing, right? And let's not overcomplicate things, right? Let's just screenshot it, plop it into Paint, right? Just pop it in there, and there we go, right? And you, smart little internet person you are, you might just check the distances between the peaks. Okay. Seems simple enough, right? I mean, just check the distances between the peaks, and you will get the wavelength. Hold on, give me a second. I'm back. Ah, that's too loud. My mixer. So, you, the smart London person you are, what you may do is you can check the peaks and then check the distance between them, right? There, these are the distances. And would you believe it? This would actually be equal to the wave function. Well, isn't that convenient, right? Wrong. It's actually too convenient because you see, this actually has a certain degree of uncertainty, which mostly stems from the fact that whilst in the middle, this entire function seems like a wave function, right? It seems to be oscillating. On the edges, it's slowly but surely getting smaller and smaller. And so, oh mate, I really need to write a script for this, because without a script, or maybe it's the sleep deprivation. Either one could be at fault here. But my point is, oh, if only we had some sort of mathematical tool which could actually, if only we could have some sort of mathematical tool which would allow us to, I don't know, check with which wave frequency, with which wavelengths this actually correlates the strongest, right? If only there was some sort of mathematical tool we could use to check with which wavelengths this function correlates the strongest. If only, right? Well, if only we had some sort of thing, if only we actually had something which allows us to get like a new function which tells us, oh, what wikipedia.org/wiki/Fourier_transform. Well, isn't that a curiosity? I wonder what that's all about. I'm having a stroke. Yeah, Fourier transform. That's precisely what the Fourier transform does. It just checks with which wave function the function correlates strongly, kind of. Oversimplification a bit, it's a bit deeper than that, but that's the gist of it. That's what we use it for when it comes to uncertainty. And the entire idea of uncertainty looks like this. That's where the second, much more complex function comes into play. How much sleep is Bro operating on? Funny story, I don't even have to guess. I don't even have to guess on how much sleep I'm operating, because I have a spreadsheet telling me exactly how much sleep I'm operating. To be fair, I have slept a lot. So today, right now it's 10 PM. There we go. And last time I slept was right here. So 26 hours ago. But that was a fair amount of sleep, right? That was 10 hours of sleep. That's good enough. That can last me a while. Festive. Cool, right? Yeah. Alright, so now it's time for the other equation, which I will call FO. Because it will be Fourier, which will input x and be equal to, oh goody, isn't this a fun one? Divide by 4 square root pi, 2 pi, because obviously I had to normalize it. I can do it like a normal person. 5 times 2 pi, because obviously I had to normalize it. 5 times 2 pi, because obviously I had to normalize it. 5 times 2 pi, because obviously I had to normalize it. 5 times 2 pi, because obviously I had to normalize it. 5 times 2 pi, because obviously I had to normalize it. 5 times 2 pi, because obviously I had to normalize it. 5 times 2 pi, because obviously I had to normalize it. 5 times 2 pi, because obviously I had to normalize it. 5 times 2 pi, because obviously I had to normalize it. 5 times 2 pi, because obviously I had to normalize it. 5 times 2 pi, because obviously I had to normalize it. 5 times 2 pi, because obviously I had to normalize it. 5 times 2 pi, because obviously I had to normalize it. 5 times 2 pi, because obviously I had to normalize it. 5 times 2 pi, because obviously I had to normalize it. You have to remember that I'm doing all of this live. Normally it's a much simpler concept. It's a bit hard to explain when you're not prepared. And then e to the power 1/2 negative, obviously. S squared x minus 1 squared. Let me copy all of this. X plus 1. Okay, there we go. Sick. And now see what happens. So basically, the red equation is telling us. The red equation is showing us the function, and the blue equation is telling us with which frequency. No, with which I keep saying frequencies, which is wrong. It's the wave number. With which wavelengths it is correlating strongly. So, for example, right now. It is correlating strongly. I think that's a technical term. I don't know. Alex correct me on that, which means even if I'm making a mistake, then it's hopefully not a major one. So that means that right now we can see that the highest, it's best correlating with wavelength of 1. Oh, that's why there shouldn't be a 3, because I made this entire thing for 1. So 1. That's what it's correlating strongly with, which means that's the kind of best fit for our equation. And as we can see, as we increase the S, these peaks get higher and higher. And basically we're becoming more and more certain that the wavelength of 1 is the right one, pun intended. But as we increase the S, what we're also increasing just how spread out this function is. Which means right now the wave is starting right here, right? This is kind of where the wave is starting, and this is kind of where it's ending. It's massive, it's just a huge wave. Which means that we are uncertain about the position of the wave. Which means that we have either spread out wave, massive spread out wave, so we're uncertain of the position, or if we are very certain of the position and we have like a single peak, then we're really uncertain of the frequency. And skibbity boom, skibbity bish, skibbity pow pow pow. If you remember from the previous adventures in the quantum mechanical world, momentum is equal to energy divided by velocity, and energy is equal to, oh goodness, what was it with K? It was something with K. Energy is equal to HK. Okay, so it was just HK and H bar as well. Energy is equal to HK, which means that the momentum is equal to HK divided by C. Wave number. Wowee! It's dependent on the wave number. And so basic idea looks like this. We can't know the position and the wave number of a wave function at the same time. But since momentum is dependent on the wave number, what this is actually saying is we can't know the position and momentum. P is equal to HK. Wait, really? P is equal to energy divided by K. Energy is equal to HK. Did I miss the... H bar K. H bar, right? But wait, H divided by C. I'm pretty certain that's not H bar. Doesn't seem like H bar. The point is, okay, the point is it's something multiplied by K, okay? Alright, there we go. Sick. Physical, yeah. So this is one. Okay, this is one example of uncertainty. There are plenty more as I've learned from Alex. But this is the most basic and most often used an example kind. And that's an uncertainty principle. And oh boy, oh, evolution of wave particles. Oh yeah, time. I love time. Now we're going derivatives, huh? Everywhere. Yeah, where I don't really care about derivatives. And, oh wait, this just gonna be derivatives. This is insane. Passively moves at a uniform velocity of. Oh no. Yeah, so we have uncertainty of position and wave number, which means position and momentum. Interesting. Wow, that is very interesting. Ah, I see. Well, isn't that a curiosity? Oh ho ho, okay. That's some certainly numbers. Which means that... okay, so we're just defining it more and Heisenberg's microscope. They bloody gone and did a Breaking Bad reference. I'm having a mental breakdown. The uncertainty principle follows from two facts. First, it's impossible to measure any property of microscopic dynamical system without disturbing the system somewhat. Second, the parting in light, energy, and momentum are quantized. Hence, there is a limit to how small we can make the aforementioned disturbance. Thus, there is an irreducible uncertainty in certain measurements. That's a banger of a sentence, I'm gonna say first. That's a consequence of the act of measurement itself. Oh, did I understand this chapter? Absolutely not. Let's move on to the next one. Schrodinger's equation. Okay. Wave function of a free particle of mass m satisfies this. Cool and stuff, and yeah. Like your Breaking Bad, neural activation. Jesse, we gotta learn quantum mechanics. Austin. Alright. It follows from equation that numbers and is derivative and then next derivative. Alright. Whereas, so in relation, okay, so the partial derivative, this is all partial derivatives. Jesse Steinkoff. You're gonna make a stream best of. Be my guest. If I have a shitpost channel if you want. Well, I can just. It's made for shitposting. Bye guys. Bye educational. On to the next job. Thanks, mate. Okay, so partial derivative, it's partial derivative because, you know, this is a capital psi, it's position and time, which means this is the partial derivative of a partial derivative of position, and then we have a partial derivative in relation to time. Sick. Thus, and then this is mad because it's partial derivative in relation to time, so this one plus h divided by 2m plus this one is equal to this one. And for I haven't solved an integral in a while. I don't remember the rules. Okay, let's understand this. Okay, I don't really understand what this is saying yet. This is simple. It's basically the How do I actually, hold on. Complicated way to motivate the Schrödinger equation. Yeah, I mean, this is, okay? This certainly is. We're used can this relation. Multiplying by h, we obtain you do what now? Oh, because it's equal to 0. Hold on, wait, let me cook here for a second. This has to be equal to 0, which means the antiderivative from negative infinity to positive infinity has to be equal to 0 dk. K is the wave number, which means, oh, this is cookable. This is edible. Hold on. This is edible stuff. So I just gotta figure out what this means. This is wave function. It's 0 inside the integral already. Why? Because of equation 212 2. Oh my god, k is equal to... Oh, you are right. How did I not see that? Okay, yeah, that makes sense. Which means right here we get 0, which means it's equal to 0. Make it music. This is actually, this isn't even mine, actually. It wasn't even made for me. It's my favorite, okay, it's my probably most often used piece of solo music, which is Iced Over. I absolutely adore Iced Over. And I do use it almost everywhere because it's just my favorite to use in edutainment videos. Yeah, and so if we get 0 right here, everything else is multiplied, which means we get 0. And if we get 0, that means we basically have this equal to 0, which basically means that we can move this onto the other side, which we do, and we can multiply both sides by h bar. This expression is also known as Schrödinger's equation, but what it means is that the partial derivative of the wave function in relation to time, so basically how the wave function changes in relation to time, is equal to this is technically mass. Let's skip over this bit for a second and this bit. And so what it's basically saying is that the partial derivative in relation to time is equal to the curvature of the partial derivative in relation to position divided by 2 mass. Bit of a high constant, whatever. So this means that the way the wave function changes in relation to time is related to the curvature of the wave function is the position divided by mass. The time evolution of particle wave function is generally easy to solve than the integral equation. Of course, equation is only applicable to 3D moving particles. Fortunately, it's fairly easy to get generalization of the equation, but it's plausible in some potential v of x. That's why v of x is added. We can identify k with the differential operator. Hence, the differential operator on the right hand side of the equation is equivalent to, oh boy, yeah, but p, which means it's p squared. Thus the operator is also equivalent to p squared divided by 2m, which is just the energy of a 3D moving particle. However, in the presence of potential, particle energy is written, thus it seems more reasonable to make the substitution. General one-dimensional function. Okay, so we have potential energy, kinetic energy, the curvature of position, the change duration time. What are we trying to find out right now? What this means, which would mean that the evolution of the wave. Hold on, this is actually. Wait, so the evolution of the wave function is equal to the energy of the particle, except the curvature is there for some reason. Yeah, according to original interpretation is proportional time. Okay, so as well, can make as much of the name value x0. We know the particle is located at 0. Yeah, how it changes in time is governed by energy. But why is this there? This right here, the curvature space, whatever. The curvature is just derivative of derivative. Wouldn't it be easy to explain in terms of operators instead of scary looking equations? Technically, but only technically. Let me show you something. Only technically, because you have hold on. Because you have this Hamiltonian. So this is just kind of the Schrödinger's equation, just the Hamiltonian. The minimum operator P is derivative. Oh, I didn't see that. Wait, yeah. So this is the momentum. Wait. So this means that the evolution of a particle is just equal to its energy. Is that really it? I want to follow you. Let's be real, we all want to follow Alex. Okay. That makes sense. On the stream I will build my cult. Yeah. The cult of the atom. Wait, isn't this really simple then? Alex open news. No competition. Make such a measurement of the value x0 when the particles located at 0 millimeters draw in common center because the particle cannot have shifted in the pressure. Thus, in the value of the first measurement, the measurement of the particle portion is certain to give the value of x0 has no chance of giving any other value. This implies the wave function must have collapsed or spike. Hold on, so measurement in the same value x0. We know that the particle is located at x equals 0. If we make another measurement immediately after the first one, common sense tells us that we must obtain the same value x0 because the particle cannot have shifted position appreciably in an infinitesimal interval time. Thus, immediately after the first measurement, a measurement of the particle's position is certain to give us a value of x0. There's no chance of giving us any other value. This implies that the wave function must have collapsed of spike function located at x equals 0. This is illustrated in figure. Of course, as soon as the wave function has collapsed, it starts to expand again. Thus, the second measurement must be made reasonably quickly at first in order to guarantee the result will be obtained. Quantum mechanics, the wave function of a particle changes discontinuously in time whenever a measurement is made. We conclude that there are two types of time evolution of the wave function in quantum mechanics. It's the smooth evolution that's given the Schrödinger equation. The evolution takes place between measurements. This continuous evolution takes place each time measurement is made. Came for make it but stay for Alex. And yeah, I came for make it but stay for Alex. Time evolution happens because of energy. After all, energy is the capability of doing stuff. pretty certain Alex isn't self-taught, and it actually shows a difference between me, who is self-taught, and Alex, who isn't. And just take a wild guess at who knows quantum mechanics better. Hi, the Great Palm. Wait, hold on. If I'm... I think I get it. I think I understand Schrodinger's equation. I mean, I will double check on the wiki, because of course I will. Because these definitions are usually a bit more, say, a bit less user-friendly. Wait, that can be derived using, yeah, derivatives, okay. Maybe just Schrödinger equation. A linear partial differential equation governs a wave function of a quantum mechanical system. Its discovery of landmark quantum mechanics. Schrödinger postulates equation. Schrödinger's equation is the quantum counterpart of Newton's second law in classical mechanics. Huh. That is literally what it's saying. That's way simpler than I was expecting. That's so simple. Oh my goodness. Oh my goodness. By the way, Alex, I've looked away for 1 second. How are you already toppling over government? What if Alex is Grant Sanderson? Oh, you don't have to tell us who Grant Sanderson is, don't worry. Secretly. Yeah, secret undercover mission by Grant Sanderson. Wait, this is so simple. Penguins can fly. Nice try, Alex. Of Alex's mission, Grant's voice. The Schrodinger's equation is so simple. Oh my goodness. I'm not free blue and brown. That sounds like something that that free blue and brown would say. How will we explain it? I mean, it really is simple. Okay, let me hold on. You wanna know just how simple this is? Let me spell it out for you, alright? You ready? Okay, ready? We'll have an equal sign in the middle. Particle change this is an oversimplification of it because it's not technically energy, but yeah, that's kind of it. It's not 3 energy, it's mostly just like maybe it is kind of, yeah, it is good enough. There we go. That's why is I in the because because waves. I mean, this is kind of it. That's kind of what it's saying, which makes sense. It's true for classical mechanics too. I mean, you know, like movement. If you have a cube which weighs 500 kilograms, then the movement of this cube is equal to the energy you put into it. Oh, we are walking in ruins now. If only we could decipher this this cryptid message. The music goes hard in intense mouth. I'm gonna send that quote, Nana. I'm gonna send that quote to Soda. I want them to know. There's an actual alternate classical theory that has an equation exactly like Schrödinger equation. Yeah, it would make sense. Looks like a joke. It's literally hieroglyphics. I mean, I guess now that I look at it, yeah, it does look rather silly, but it's runes. This is insane, right? Run Ultra Instinct Goku theme song. It's completely equivalent to Newton's law. I mean, it's not that crazy to think that way, right? Because, for example, just like most people think of velocity as just meters per second, or miles per hour if you use the British system, right? In reality, what it is just derivative position in relation to time. And this is the same way we do it in quantum mechanics. The thing is, quantum mechanics is just more precise by default. In classical mechanics, the precision is just an additional thing. Let me try to prove this equation, or do we just think it's true? We just witnessed the proof. I just glossed over it because it's just genuinely hard. It's a genuinely difficult and complex proof. I'm pretty certain it's proof. I know. I understand. From ancient Greek poetry. Yeah, it's actually a tale about Loki trolling Thor. There we go! That's Tronigus for ya. That was fun. How many slash I'm going for? Oh, I'm so tired. Well, that was fun. And let's all now take a second. Let's take a minute. Essentially showing about the wave functions. I don't know if wave function is gonna help much. It has to keep the derivative something, so tend to the derivative of a derivative kind of. You know. Alright, everyone, it'll be about time to end the live stream. So let's first collectively take a minute to thank Alex for being the sole reason for why we actually got this far. Now, remember, if you want to sign up to the Cult of Alex, the registration will take place in between 3 to 9 p.m. Standard Pacific time on a Wednesday, Thursday, Friday, and a Sunday. So just join in, look in all the dark alleyways, and the Church of Alex will be also accepting donations. Now, please remember inside cold entry forms on the way up. Precisely. As far as your sleep spreadsheet, it's not. I mean, it's not really sleep spreadsheet. It's my productiveness spreadsheet. And it's kind of cool. Well, it's 10:45 at this point. 20:45. So this is where we are now. and this is my sleep. Which means I've just spent, well, considering that will take me, I will still have to script the end of the video. So yeah, 27 hours with no sleep. Could be worse. Could certainly be worse. You have until release deadline. I don't have a deadline at this point. I'm just working on as many videos as possible, as efficiently as possible. I have a progress tracker to make sure that I do make enough progress on videos, but that's it. I don't have a deadline because, as I actually found, deadlines are really inefficient for me. Because then I have to, release some videos before they are ready. I have to wait with releasing others, so yeah. Share the spreadsheet, make it. Come on, don't be shy. Yeah, I would love for all of you to just have a self-updating page which tells you exactly what I'm doing at the moment. That's not 10 days of no sleep. See? Tilly gets it. In that case, I can run you a nice 3,000 page book on quantum theory. Sounds like a blast. I'm already immune against caffeine. It was. I went through a detox recently. It was hell awful. Absolutely wouldn't recommend. But at the same time, before the detox, I was taking 500 milligrams of caffeine a day. So half a gram of caffeine a day, which let's just say it's not the healthiest option. So I guess the detox was kind of important. I don't know when you are sleeping. That's so creepy, my guy. A guy, even I will. Are we ending? Yeah, we are. But I'm just so bad saying goodbyes. Give the spreadsheet to fortune, they will find you. Please don't. I'm just trying to make videos. I need to know when you eat your lunch. I need to know. I don't really have a time for eating. I just eat whilst doing all the stuff because it's more efficient. Anyhow, well, that was a productive live stream. And I think it's about time that we part our ways and go do what we're meant to do. So, we did manage in the very end. We tried to study quantum mechanics and we did manage to make it happen. For now, that'll be it. Thank you everyone so much for watching and have a great day. Bye.